Hello, in this video I am going to explain optical fibers which comes under module 3 of video syllabus. Here I am going to discuss about total internal reflection, expression for numerical aperture and also condition for propagation. So now let us concentrate on total internal reflection. So when a ray of light travels from denser to rarer medium, it bends away from the normal. As the angle of incidence increases in the denser medium, the angle of refraction also increases. For a particular angle of incidence called the critical angle, the refracted ray grazes the boundary separating the media, or the angle of refraction is equal to 90 degrees. If the angle of incidence is greater than the critical angle, the light ray is reflected back to the same medium. This phenomenon is known as total internal reflection. In total internal reflection, there is no loss of energy. The entire incident ray is reflected back into the same system. So now consider a diagram. So let us consider a picture. So I am going to show that in the next slide. So here xx dash is the surface separating the media of refractive index n1 and a media of refractive index n2. So here the refractive index n1 is greater than n2. Let us consider a beam that is AO and it gets refracted along OA dash. So here AO and OA dash are incident and refracted rays. And theta 1 and theta 2 are angle of incidence and angle of refraction. So it is observed that theta 2 is greater than theta 1. For the ray BO, that is the second beam, so theta c is considered as the critical angle of incidence such that OB dash is the refracted ray which grazes the boundary. The another ray, that is the third ray CO, incident with an angle greater than the critical angle theta c such that it will undergo total internal reflection and reflect back into the same system, and it is gets traveled along OC dash. So now you can look at the process in this picture. So here is a diagram. So the first beam BO with, so the first beam is AO here with an angle of incidence theta 1 and it gets refracted along OA dash with theta 2. And the second beam is BO, the angle of incidence is theta c and it gets refracted along OB dash. So here the value of theta 2 is equal to 90 degrees. The third beam is CO, which gets reflects back into the same system and travels along OC dash. So here the angle of incidence is greater than the critical angle theta c. So the third beam undergo total internal reflection. So here the refractive index of first medium is greater than the second beam, that is n1 is greater than n2. So next slide. So if we apply Snell's law for the incident beam 1, we can write n1 sin theta 1 is equal to n2 sin theta 2. So for the second beam, theta 1 is equal to theta c and theta 2 is equal to 90 degrees. Then the same equation takes the format n1 sin theta c is equal to n2 because sin 90 degree is equal to 1. So finally the value of theta c is equal to sin inverse n2 by n1, that is the critical angle. So in total internal reflection, there is no loss or absorption of light energy. The entire energy is returned along the reflected light. Thus, it is considered as total internal reflection. Next, here I am going to discuss about what are optical fibers, how they were all designed. So optical fibers are designed in such a way that light energy launched at one end will undergo total internal reflection within the fiber and reaches the other end with negligible energy loss. That is, light propagates through optical fiber by means of total internal reflections. Total internal reflection is the phenomenon in which light traveling from denser medium to rarer medium for a particular angle of incidence which is greater than the critical angle, so it will undergo total internal reflection. This kind of refraction in which light reflects back into the same system. Okay, so the optical fibers are consists of core and cladding, where core material is having refractive index greater than that of cladding material. In the next slide, I am going to show you how the ray propagates. So here is a picture. When light is made to incident at certain angle and enters the core, okay, for a particular angle of incidence, say theta naught, the light ray will undergo total internal reflection at the boundary of core and cladding, which is possible here because N1 is greater than N2, where N1 is the refractive index of core and N2 is the refractive index of cladding. And here theta naught is the angle of incidence measured with respect to the fiber axis, and it is considered as acceptance angle. So here in the next slide I am going to show you the schematic diagram of optical fiber. So here it is cylindrical in nature. The central part is core, the outer part is cladding, which is encased in a polyurethane jacket, and the refractive index of core is observed to be larger than that of cladding. So this is what the schematic diagram of optical fiber. So next slide, let us discuss about the expression for numerical aperture and condition for propagation. So here is a picture. So you can look at core and cladding. The refractive index of core is N1 and that of cladding is N2, and it is kept in a media whose refractive index is N0. Now consider a beam of light entering the optical fiber at A, that is along OA, with an angle of incidence a theta naught, such that it gets refracted by making an angle theta 1 with the fiber axis as shown in the diagram, and it falls at core cladding interface at B at an angle say 90 minus theta 1. Because of that, it will just grazes the boundary, that is BB dash as shown in the diagram. So the next slide, you can look at the way they were all placed. So here N0 be the refractive index of the surrounding media in which the optical fiber is placed. N1 is the refractive index of core medium and N2 be the refractive index of cladding. And it is observed that N1 is greater than N2. Now let us consider OA is the light incident at an angle say theta naught and enters the optical fiber at A. Okay, and let us consider AB be the refracted ray at an angle say theta 1 within the core. Let theta 2 be the angle of incidence made by the ray AB at B on the boundary separating core and cladding, such that theta 2 is the critical angle for pair of media core and cladding. As we have discussed or assumed theta 2 is critical angle, AB is the ray refracts along the boundary separating core and cladding, that is considered as BB dash. Now by applying Snell's law for the beam, that is first beam entering the optical fiber, that is N0 sin theta naught is equal to N1 sin theta 1, that is for the beam 1 which is entering the optical fiber. So consider this as equation number 1. Similarly, by applying Snell's law for the refracted beam at B, we can write N1 sin theta 2 is equal to N2 sin 90 degrees. So sin 90 is equal to 1, so it will become N2. So it is observed that theta can be written as theta 2 can be written as 90 minus theta 1 as per the geometry. Therefore, we can write N1 cos theta 1 is equal to N2. So that is considered as equation number 2. From equation 1, we can write sin theta naught is equal to N1 sin theta 1 divided by N0, or N1 into square root of 1 minus cos square theta 1 by N0, because sin theta 1 can be written as square root of 1 minus cos square theta 1. So here in place of cos theta 1, we can write N2 by N1. So after simplification, we are going to arrive at the expression, that is N1 by N0 into square root of 1 minus N2 by N1 whole square is equal to square root of N1 square minus N2 square whole divided by N0. So finally, the value of sin theta naught is equal to square root of n1 square minus n2 square whole divided by n0. Here, theta naught is considered as angle of acceptance and sin theta naught is called numerical aperture, which is measure of light gathering capability of an optical fiber. Therefore, the numerical aperture NA is equal to sin theta naught, that is equal to square root of n1 square minus n2 square whole divided by n0. And further, the acceptance angle theta naught is equal to sine inverse of square root of n1 square minus n2 square whole divided by n0. If the surrounding media is air, then the value of n0 is equal to 1. So this is what you have to remember. So now I am going to discuss condition for propagation. For the expression of numerical aperture, that is NA is equal to square root of n1 square minus n2 square, for any angle of incidence equal to theta I, which is less than or equal to theta naught, the incident ray is able to propagate. That means it will undergo total internal reflection. That means theta I is less than theta naught or sin theta I is less than sin theta naught. So sin theta I less than numerical aperture is considered as condition for propagation. So next concept is fractional index change. So it is nothing but the ratio of refractive index difference between the core and cladding to the refractive index of core of the optical fiber. That means fractional index change denoted by symbol delta, that is equal to n1 minus n2 divided by n1. So next I am going to discuss about the relation between numerical aperture and fractional index change delta. The fractional index change delta is already written as n1 minus n2 by n1. Consider that as equation number 1. So here n1 is the refractive index of core and n2 is the refractive index of cladding and n1 is greater than n2. And we have one more expression, that is numerical aperture is equal to square root of n1 square minus n2 square. Consider that as equation number 2. So you can write n1 square minus n2 square as n1 plus n2 into n1 minus n2. That is the mathematical expression. So it will be written as square root of n1 plus n2 into n1 delta, because n1 minus n2 is nothing but n1 delta. Generally n1 is equal to n2, so n1 plus n2 can be written as 2n1. Therefore numerical aperture is equal to square root of 2n1 square delta, or numerical aperture is equal to n1 into square root of 2 delta. So this is what the relation between numerical aperture and the fractional index change delta. Next concept is V number. The number of modes supported for propagation in the optical fiber is determined by a parameter what is called V number. The number of modes sustained in an optical fiber depends on the diameter of the core, that is small d, and refract index of core, that is n1, and the refract index of cladding, that is n2, and also lambda, that is the wavelength of light used, which can be calculated by a parameter what is called V number, given by V is equal to pi d by lambda into square root of n1 square minus n2 square. If the fiber is surrounded by a medium of refractive index n0, then we can write V is equal to pi d by lambda into square root of n1 square minus n2 square whole divided by n0. For a value V greater than 1, the number of modes actually supported by the optical fiber will be equal to V square by 2. So in this way we can able to calculate the number of modes supported by the optical fiber, that is equal to V square by 2. So in the next slide I am going to explain the types of optical fibers, attenuation, and also applications of optical fibers. Thank you.